In this video cast, we will look at why and how electrons spontaneously flow in an electrochemical or a redox type reaction. We'll begin by taking a look at this redox reaction, and we'll take a look at it in terms of separating it into its half reactions and putting those half reactions into different cells, or in this case different beakers, and connecting them via a wire and also via something called a salt bridge. In this particular redox reaction, we're going to take an amount of potassium iodide and put it into this beaker, and then we'll take an amount of potassium dichromate and put it into this beaker. It will form this redox reaction down here. And some of you might look at this redox reaction and say, yeah, but what happened to the potassium? And you'd be correct, but take a look at what type of reaction this is. This is a net ionic equation where only the reactants and products that actually do something in the reaction are here. When Ki is put into solution, it will dissociate and form K plus ions and I minus ions. The K plus ions simply spectate, and therefore they're not a part of the reaction. So the sources of ions that we're going to look at in this particular reaction are Cr2O7 2- and the I- ion. And we're going to look at how those two in separate containers can still undergo a redox reaction even though they're not in the same beaker. So reading this question, it says the redox reaction is spontaneous. A solution containing the potassium dichromate and a bit of H2SO4. The H2SO4 is a good source of H plus ions that we use to balance this redox reaction. It's poured into one beaker and a solution of Ki is poured into another. Salt bridge is used to join the beakers. A metallic conductor that will not react with either solution, such as platinum foil, is put into each. Two conductors are connected to wire through a voltmeter or some other device to detect electric current. The resultant voltaic cell generates an electric current. Please indicate. So why do the electrons spontaneously flow in a setup like this? Well, it turns out that there's a certain amount of potential energy per unit charge, or a potential difference, or a difference in potential between these two electrodes, or these two beakers, you could say. One of them has more potential for attracting electrons, and one has less potential for attracting these electrons. These have been categorized and measured as something called standard, reduction, potentials. And we've looked at these before in a table. You've probably seen a table something like this before, where they give a big long list of possible reductions that can occur, and they rank them. And notice the units happen to be in volts as well. This is the type of table you'd see on an advanced placement exam, and it gives you the reduction of many different elements to its reduced species, and then it tells you the potential that it could be reduced in voltage. And notice the higher voltages are at the top, and the lowest potentials down here at the bottom. Remember, reduction and oxidation are opposites of each other. So things up here at the top have great potential to be reduced, whereas things down here at the bottom have great potential to be oxidized. So these also could be considered to be an oxidation type potential table, except you'd have to read it from the bottom, being the greatest potential to be oxidized, and the top being the greatest potential to not be oxidized. We'll look at those tables again in just a second. But let's get back to the problem. The problem asks us to find the reaction at what's called the anode and the reaction that's what's called the cathode. Well, the anode is defined as where oxidation takes place. Oxidation starts with an O, anode starts with an A, both vowels. So you can always remember anode oxidation because they start with the same type of vowel, or they start with a vowel. Cathode is defined as where reduction takes place. You can remember cathode reduction by remembering red cat, something that's reduced as at the cathode. It's a good way to remember the cathode is where they're reduced. So what type of reaction is taking place? If we look at this one and separate into its half reactions, we'll notice that Cr2O7 minus is coordinated with 2Cr plus 3. And we can see that chromium, when it's assigned here, has a +6 charge, and it's reduced to a +3 charge right here. So this is our reduction half reaction. Of course, I'd have to add the 7 waters in over here to help balance the oxygens, and that's what the 14 hydrogens are over here to complete the entire balanced half reaction. So this is the reaction that would happen at the cathode, because reduction is defined as occurring at the cathode. Okay, our other reaction that's happening is our iodine, 6I minus, is going to 3I2. And we can see that -1 iodine is going to 0 charged iodine solid. And so we have oxidation going on here, and this is what would occur at the anode. So our anode is over here, and our cathode occurs right here. Next question they ask is, what is the direction of the electron migration? Well, the thing that's losing electrons will give them up, and we know that our iodine right here actually is losing electrons. I didn't put the electrons in the half reaction, but you can see that they would lose the reaction, the electrons. And our I minus is becoming I2 solid, and it's giving up an electron. These electrons flow spontaneously and are attracted to the thing that is being reduced. And so the electrons flow spontaneously through here in this direction from anode to the cathode. The next question is, what is the direction of the ion migration? Well, to make this cell work, we can't just have one electron go over here and then plunk itself down into this solution, because we'd have an imbalance in charges going on here. And so there has to be some way to replace the negative ions that are lost here, and to equal out or even out the electron, the negatives that are brought here. Since negative electrons are brought into this electrode, we have to have the salt bridge equalizing it out by having cations, or positively charged ions, flow this way. And to replace the negative ions, or the electrons that are lost over here, we have to have the negative anions flowing this way, flowing from the salt bridge into this solution right here. So that's the direction of the ion migration in the salt bridge. What would happen if you took a salt bridge out? Well, of course, then the electrical current wouldn't flow anymore, because we'd have an imbalance in charge. One electron would bump itself down here. It could no longer run. And then lastly, the signs of the electrodes. The signs of the electrodes are assigned arbitrarily in that we assign the cathode the positive charge in this case because it attracts the electrons to itself. You can think of it this way as well, that the anode is giving away electrons, so it's got a great buildup of electrons that are being pushed this way and attracted to the positive charge over here. So that's the that is a voltaic cell. And now we're going to take a look a little bit more at some more voltaic cells and ask some other questions about these and get into the quantitative nature of these as well. In this sample problem, it says, given the standard reduction potential of zinc to Zn solid being negative 0.76, calculate the reduction potential for the reduction of copper +2 to copper. Well, we're also told that the entire voltage, or E of the cell itself, is 1.1 volts. Now, we can calculate the voltage of a cell with this equation. E of a cell, usually we calculate it at what's called standard conditions, 25 degrees Celsius and in 1 molar solutions, 1 atmosphere if we have a gas, is equal to the standard reduction potential for the cathode minus the standard reduction potential of the anode. Now, books define this in different ways, but our book always takes cathode minus anode to find the cell voltage, or the potential difference in the cell, cathode minus anode. The reason they use an E for this is because E is short for EMF, which stands for electromotive force. It's the electron moving force, or the force moving the electrons from one point to the other. Well, since we know this equation, we can say that the cell voltage is 1.1 volts. We can look and see that the cell has zinc plus 2 going to Zn solid. And so we'd say that that is zinc being reduced. Okay? If you look at the cell itself, though, this is the reduction potential, and this is what we'd find on this chart right here for zinc going to Zn at negative 0.76. Whoops, maybe you can see it right here. Okay, there's the standard reduction potential for it. But if you look at the actual reaction for the cell, you see that zinc right here goes from zinc solid to Zn plus 2, which is oxidation. Zinc being oxidized right here would be what's called our anode. So our anode is located right here. And in our equation, our anode would have a value of negative 0.76 volts. Now, we don't know the standard reduction potential for the cathode, and our cathode in this case is copper going to copper plus 2, going to copper solid. And so solving this equation now, I have 1.1 is equal to the standard reduction potential for copper minus a minus 0.76. If I solve this, I'll have 1.1. Now a minus, remember, becomes a plus. So I'll subtract 0.76 from this side and subtract 0.76 from this side. So 1.1 minus 0.76 is equal to the standard reduction potential for our copper. And if I do this math, I think I come close to having a standard reduction potential for copper of 0.34 volts. Let's take a look at another problem. This one says that line notation is sometimes used to identify each cell in an electrochemical reaction to list its components as follows: anode, anode solution, cathode, cathode solution, cathode solution, cathode. The double vertical line represents a salt bridge, or a porous barrier that allows the free flowing of ions. A single vertical line represents a change in phase, such as from solid to a solution, or it could be from a solution to a gas as well. If both aqueous substances are 1 molar, indicate the reaction at the anode, the reaction at the cathode, the direction of electron migration, direction of ion migration, the signs of the electrodes, and calculate the EMF of the cell. So let's use this picture right up here to represent this cell that's going to happen. And remember that the anode and anode solution are listed first. Remember, anode is where oxidation takes place. Cathode, cathode solution, this is where reduction takes place. So if this is our oxidation, that must mean zinc must be going to zinc plus 2 in the anode solution. This is already labeled anode for us, so we'll just fill it in and say that our zinc is becoming our zinc plus 2. This is our zinc solid, and it must be becoming the zinc plus 2. In other words, after this cell runs for a while, this zinc will, in effect, be dissolved and become zinc plus 2. this electrode would actually become smaller as the electron, as the reaction continues to occur. Now on this side, we can see that we've got a second reaction of H plus going to H2. And when that happens, we should have our H plus going to H plus 2. And so this must be where our H is building up right here. Our H2 is building up on the cathode. And then we've got our H plus in solution. Okay, H plus is being reduced to H2. You can see this is our reduction, known as the cathode, red cat. And this is our anode, or our oxidation. Okay, anode, oxidation both start with vowels. Okay, let's see. Going on, we've got the reduction at the anode. We've got our, our oxidation at the anode and our reduction at the cathode. Next, it says, what's the direction of electron migration? Well, the thing that's losing electrons is the thing that's oxidized. Oxidation is loss. Since we're losing electrons, electrons must flow from here through here, and it's attracted to the cathode. We can see that the cathode has a positive sign, the anode has a negative sign. Cathode positive sign, anode negative sign. The ions must migrate to, this is letter G now, the ions must migrate to take care of this extra electrons that's being brought in here. And so the cations must flow in this direction, and the anions must flow in this direction. Signs of electrodes, and lastly, we're supposed to calculate the cell EMF. To calculate the cell EMF, what we need to do is take the cathode standard reduction potential minus the anode standard reduction potential. And if you look on your list of standard reduction potentials, hydrogen right here, H plus going to H2, has a standard reduction potential of 0. Okay. That's our cathode, so we'd put 0 in. And then looking up our anode, which is zinc, we'd find where zinc plus 2 goes to zinc solid, and that has a reduction potential of negative 0.76. Negative 0.76. So we take this minus 0.76 and we'll end up with a voltage of positive 0.76 volts. This positive sign actually is really important. It tells us a lot about this redox reaction. Any redox reaction that has a positive voltage means that it is spontaneous. Spontaneous in the direction that it's hooked up, or it's spontaneous in the direction that it's that we defined it as. And of course, if it's spontaneous, if you remember from chapter 19, that means that its delta G must be negative. And so using the voltage of a cell, we can actually calculate delta G, and we'll do that in a problem in just a little bit. On this side of, on the next page, there's actually a few more exactly the same type of problems where you calculate the standard EMF of a cell. And here's a second one where a voltaic cell is based on another one with line notation. And then down here it actually asks some questions about standard reduction potentials and the ability of something to act as an oxidizing or a reducing agent. We'll continue with these problems on the next clip.